So welcome back. Just before we ended the previous module, I was telling you that the next topic that we'll talk about is the representation power of a multilayer network of sigmoid neurons. So let's understand what I mean by that, right? So just a quick recap, right? So earlier, when we were finishing perceptrons, we had introduced this multilayer network of perceptrons, and we had spoken about the representation power of a multilayer network of perceptrons. Analogously, now we are going to talk about the representation power of a multilayer network of sigmoid neurons. It's just the same template being repeated, right? And there we had made an interesting statement, right? That a multilayer network of perceptrons with a single hidden layer, and I don't care about the number of neurons in this layer. I know that it can be exponential, but I don't care about that. A single hidden layer can be used to represent any Boolean function precisely. And the meaning of that was that if you have an n variable input, then you would have a Boolean function of n variables, and it would have a certain truth table. Now, no matter what the truth table is, right? And we had seen that for an n variable input, you could have 2 raised to 2 raised to n functions. So any of these functions, you can come up with a network which can precisely represent this function. That means when you give a certain input configuration, the network can produce the same output as is mentioned in the truth table, right? And the way we were doing that is by having these exponential number of neurons in the hidden layer, such that every neuron was like specializing for, or every perceptron was specializing for one specific input, right? So that's what the representation power of a multilayer network of perceptrons was. Now my goal is to make a similar statement, okay? And this, of course, we had proven by construction, right? We just constructed a network, and we were convinced that it can actually represent any network, irrespective of whether it's linearly separable or not, right? Now my intention is to make a similar statement for multilayer network of sigmoid neurons, right? And the statement is multilayer network of neurons with a single hidden layer. So far so good, it's the same as what I see on the left hand side, can be used to approximate. Okay, now here are where the differences start. So this was represent, now I'm saying approximate, right? So that means that it's not going to be exactly equal. Any continuous function, this is good news, right? Because here I was only talking about Boolean functions. Now any continuous function, right? Any function f of x which is continuous, I can approximate it to any desired precision. Now what does any desired precision means, right? So the way you would have seen this in many mathematical proofs, right? I would define a threshold epsilon, right? And what I'm saying is that you choose whatever value for epsilon, right? It could be 0.0000001, it could be 0.10001, right? And I can come up with a network such that if my network output, right? So this is the situation, right? I have a n dimensional input. I'm calling it Rx, which belongs to Rn, okay? And I'm going to design a network. I don't know what the network looks like. And the network is going to give me a certain output. Let me call that g of x. So far I've been calling it at f hat of x. I'm just calling it g of x, right? And I know that there is some true function also, such that when I take this input and pass it through the true function, I get the output as f of x. What I'm saying is that, what this statement is saying, that I can come up with any network. I can come up with a network such that the difference between the true output, okay, this is how I'm quantifying the difference, right? I'm just taking the difference between these two values. If these are real numbers, I'm just talking about the absolute difference between those two real numbers, right? Would be less than epsilon. Okay, so I would be able to approximate it up to the precision of epsilon for any of the inputs that are possible. I'll pass it through my network, I'll get a g of x, and I'm confident that it will not deviate from f of x more by epsilon. And I can construct such a network. You give me an epsilon, I'll give you a network which will produce an output which is within an epsilon from the true output, right? And of course, as you can imagine, just as we had the case there, that we had this exponential number of neurons, you could imagine, and we'll see that in more detail, that as the epsilon becomes smaller and smaller, you will need a more and more powerful network. That means you will need more and more neurons in this hidden layer. This may not be obvious right away, but this idea is something that we will develop during this lecture. Okay, so now let me just delete this and let me just put it on the slides. So in other words, I'm just going to read it out as it is. In other words, there's a guarantee that for any function f of x, that's what I was showing, that is a function which takes an n variable input and produces an m variable output. In my example, m dimensional output. In my example, m was just 1, right? I was just producing a single dimensional output. We can always find a neural network with one single hidden layer and many neurons, right? I don't know how many neurons it would have, but I can find a network with a single hidden layer and a large number of neurons, such that the output would always satisfy this condition, right? Now, this is a very, very powerful theorem, right? And this is what makes deep learning so attractive, right? So, what is it saying, right? Take any complex real-world function that you have. Let's return back to our oil mining example, where f of x was very complex. We did not even know what f is, and we know that it's a very complex function based on your input variables such as salinity, pressure, temperature, marine diversity and all that. And it's very hard to know what that function is. But now I can come up with a neural network which, when takes an input, its output would be very close to the desired function, right? In theory, I can do that. Of course, the practical difficulty is that such a neural network would have a hidden layer with a very large number of neurons. And if it becomes exponential, then we know it's not practical, right? But at least theoretically, I can do that. And this is only talking about a single hidden layer, right? And one of the things that maybe you will see through an assignment or in a quiz or something is that if you had one more layer, then you could reduce the number of neurons in each layer, right? So from exponential, it will fall down to something which is linear, which is manageable, right? So that is a separate topic. But right now, remember, we are talking about this constrained case where we are saying only a single hidden layer, okay? So that's what we want to be able to prove, right? And this is the famous Universal Approximation Theorem. And the actual proof would be a bit difficult, but what I'm going to show you is an illustrative proof which would be good enough. Just as we had seen a proof by construction. It was actually an illustrative proof. I just constructed a network and convinced you that this statement is true. I'm going to do something similar here, right? And whatever I'm going to do here is based on this excellent illustration, right? This link that you see in the bottom, which is an online textbook, one of the very early online textbooks on deep learning. And it has a very good text and an accompanying illustration explaining whatever I'm going to explain on the slide. So all the material that I'm presenting here, the ideas are borrowed from there, right? So just wanted to acknowledge that as well as point you to that resource. Okay. So this is what an arbitrary function looks like, right? So I have my input x, I'm dealing with, so this is the x-axis and this is my f of x or y-axis, right? And you can see that I have a very arbitrary looking function, right? It's maybe, it's not a sine x, it's not a cosine x, it's maybe a mixture of some of these functions, right? It's not x square, x cube, or any of the standard functions that you might know. Now, we are interested in knowing that if this is what my true relation is, can I come up with a network of neurons that can represent this arbitrary function to a certain desired degree of precision? Okay, that's what I want to do, okay? So let's see how I go about it. So what we observe is that such an arbitrary function can be approximated by several tower functions, right? So these are what I call as towers, okay? And I have constructed towers of certain widths, and it should be obvious that, so this sum of all these towers, right, or the function that you see here, outlined here, okay, and I can just go on, is what my approximation of the original curve is. And you can see that this is a slightly poor approximation, right? I am close at certain points, but I am also far from the curve at certain points, right? A case in point being this, right? So at this value of x, the actual function tells you what the orange curve tells you what the actual function value should be, but my approximation would predict it as this, right? Let me just change the color. Right? So this is what my approximation would predict it as, but the actual value is this, right? So there's a gap, right? But now, interestingly, right, if I've used a certain number of towers here, right, and let me just delete this. Now, if I increase the number of towers, oops, Right? This, as you can read here, is a poor approximation. As I increase the number of towers, right, my approximation becomes better and better. Right now, you can see that the sum of the towers that I have, right, I'm just calling it a sum of towers because I have many of these individual towers, and I've just added them. They're just all at displaced locations, and when I add all of them together, as you will see on the next slide, I get this function back, right? And now when I'm using a large number of towers where each tower is very narrow, then my approximation is becoming better, right? So this slide as such has nothing to do with neural networks so far, right? So don't try to connect it to, oh, what does this mean in respect to sigmoid neurons, perceptrons, nothing. We're just trying to make a basic observation that any arbitrary function, I could approximate it by a series of tower functions, right? And the reason I like this is that, see, all of these, whether I look at this tower or this tower or this tower, they're all rectangles, right? Only their widths, only their heights are varying, and their position on the x-axis is varying, right? But otherwise, they all have the same form, which means they are rectangles, right? So they are like the same function family. So if I know how to construct one tower, I can scale and displace and construct as many towers that I want, right? So that is something that I like, that the building block is very simple. It's just a rectangle. If I can understand how to make one rectangle, then it's just about making smaller, bigger rectangles and placing them at different places on the x-axis, right? So that is something that I like about this idea here, right? And we are going to take it further. The other thing is that as I increase the number of towers, which eventually will kind of connect back to increasing the number of neurons that you have, I can get better and better approximation. So that's where the idea that if you give me a particular epsilon, I'll be able to find a network. We have not gone there yet, right? But if you give me a particular epsilon, you can see that at least in this pictorial illustration, right, I can get better and better, right? I can make the approximation as good, and I've stopped the slider here, but you can imagine there is still scope of reducing the width of the rectangles, in which case my approximation will become even better and better, right? Okay, so I'll move ahead from here. Yeah, more the number of such tower functions, better the approximation. Okay, so now this is what has happened on the previous slide. I had this. I constructed a tower and I placed it at a certain position on the x-axis, and that is where it is. I constructed one more tower. It was at a different position, one more tower at a different position. So I've just shown you some of the towers in those large number of towers that I had, right? Now you could imagine that I would have one more, right? Say one more tower here, which would look something like this, and which would go up and come here like this, right? So I have not shown you all the towers that were there on the previous slide, but this is what is happening, right? You are constructing many of these towers independently, then just adding them all up to get the main function that you are trying to approximate, right? And all of these are similar except for their position on the x-axis and for their heights or lengths, as you may say, right? Okay, so this is what we have come to. So now if I take an input, and if I know I have been given an input x, if I have a magical box called the tower maker, okay, so I will make a tower. I have as many such boxes as I want, right, which are making these towers, okay, and then I pass all of these towers. So there is a tower maker, right, it is taking an input, okay, and it's just making a tower. All of these boxes are identical in what they do. The only difference is the amplitude or the height and the position, right? But otherwise, they are all tower makers. If I get all these tower makers and if I add them up, then I can construct my original function back, right? That's the idea. So what I'm looking for now is this fundamental unit called the tower maker. If I have that, then I have given you a network which can approximate a given function to any arbitrary degree of precision, right? This is exactly the cartoon version of the network. Now you need to concretize it. Why is this the cartoon version of the network? It takes an input x, okay, and it gives an output which is f of x, which is an approximation of the original output. The thinner my towers, the better the approximation would be. So I could control that knob. Now the only thing missing here is what the tower makers are, right? So I give the input, make the towers, add them all up, and that's what my network is looking like. Okay, so let's see. Okay, so our job now is to figure out what this tower maker black box is. Okay, so we'll figure that out. So let's start. yeah, let me just see what I want to do on this slide. Yeah, so I have an input x. Let me just explain what all is obvious here. I have the input x, okay, and I have two parameters w1, b1, w2, b2. So you have been looking at these parameters. So these two neurons that I have drawn here are going to be sigmoid neurons. So they are going to take an input x and they are going to just simply do 1 over 1 plus e raised to minus w1 x plus b1. That is what this neuron is going to output, and the other neuron is going to output 1 over 1 plus e raised to minus w2x plus b2, right? So these are both sigmoid neurons, okay. Now, having clarified that, now let's see, okay. Now what I want to do, I wanted to make a few changes here. Let's see. So first thing I'll do is I'll just make b1 and b2 0. Okay, that will simplify some things for me. Nothing wrong in doing that. Okay, it's a bit hard to do this with the mouse. Okay, so b1, b2 I've made it 0. Okay. Now you can see I can show h11, I can show h12, I have show h21. All of these are hidden right now. Okay. So let me just say show h11. Okay, so I'll just show h11. So it's looking like a straight line. As I said, it's a sigmoid function, but surprisingly it's looking like a straight line, and it's not hard to see why, because the formula for the sigmoid function is 1 over 1 plus e raised to minus w1x plus b1, right? And now if w1 is 0, right, then the x does not matter. Irrespective of what x is, it will give the same value. And what is that value going to be? 1 over 1 plus e raised to minus b, and b1 is also 0 in this case, so it's just going to be 0.5 irrespective of what the x is. Hence, throughout the x-axis, the value of the y function is a 0.5, or the value of h11 is 0.5. It makes sense, right? Now, to make it really a meaningful sigmoid function, I'll have to change w1, make it non-zero, and as I make it non-zero, you can just see, right? And as I move from 1, it's still a very gentle slope, right? It's not steep, and as I keep increasing w, right, the slope becomes steeper and steeper to the point of almost becoming like a step function, right? As I keep increasing, it almost becomes like a step function, right? So this is how the sigmoid function looks like. And if you have a very large, the takeaway is that if you have a very large w, then you actually recover the step function, right? You get the step function. Okay, so this is what h11 is looking like. Now, let me take b2 a bit higher so that I can show you the difference between them. Now, let me show h12. Again, for now, it looks like a flat line because my w2 is 0. So, let me increase w2, okay, and you can again see that it will become closer to the step function, right? And as I adjust b, it will move to the left or the right, right? That's what the b function does. It tells you the point of crossover, right? From at what point it will start going from 0 to 1, right? So that's what the b controls, okay? And now I want to do, I've defined h21 as h11 minus h12, right? That's how I've defined it. So let me just do this here. So I'll show you h21. Oops, maybe not this way. Yeah, okay. So now let me just hide the other ones. I'll reset everything and just show you h21. So this is looking like a tower function now, right? So this is the kind of tower that I wanted. It's not a perfect tower, but it's also because my two functions did not become completely step function. If I make w's very high, then you can see that it will become closer and closer to a tower function, right? It will start looking like an impulse, right? And I could increase b to increase the width of the tower. So now it's looking more and more like a tower function. So I've got my tower maker. What is my tower maker? Take one sigmoid neuron, take another sigmoid neuron, set the w's very high, right? If you set the w's very high, then you recover the step function. And then what you are essentially doing, let me just show that also. Let me reset and show this one. How did you get the tower? Because you are doing the red function minus the blue function, right? That's what you were doing. Red minus blue is what you were doing, right? So now at this point both are 0. Here both are 0. So all of this will remain 0. You are doing 0 minus 0, right? At this point both are 1, right? So again from this point onwards you will get 1 minus 1, which is 0, right? And in this region the red curve is 1 but the blue curve is 0. So in this region you will get 1 minus 0, which is 1. So hence you will get a tower like that, right? So that's the reason you are getting that tower function, right? I'll just redraw it. Right? So this is the reason you got the tower function. Okay, so that's why I have set it up that way. So now I have got a network which can produce a tower function, and not just any network, it uses my sigmoid neurons. I just have to set the W's to a high value and I can control the B's to control the width of this tower function, right? So let me just show you that. Now if I make, okay, now if I increase the gap between the B's, okay, then the width of the tower function increases. If I make it very small, of course the length also decreases, the height also decreases, but the width also decreases. So I can use the B's to control the width of the tower function, right? So that's what is happening here. Okay, so now I have got my tower maker that I was looking for. So let's go ahead, right? So this was a basic tower function. Now let's look at the entire network. So you have X, you have two sigmoid neurons. The first one will give you a step function because you set the W to very high. The second one will also give you a step function which will give you a W very high. Then you subtract one from the other, right? So you have plus 1 as the weight and minus 1 as the weight. So that's the same as H11 minus H12, and that would give you a tower function, right? So that's, I've come up with a neural network now, right, which will give you the tower function. And what is H21? What will you use for H21? Nothing. It's just a linear function, right? So it's just taking this input, it's just taking the weighted sum of its input. So I'll just call it as Wi H1I is what it is doing, where Wi is equal to 1 to 2 and W1 is equal to 1 and W2 is equal to minus 1, right? So that's all that H21 is doing, right? Just taking the weighted sum of its input, and the weights have been hand coded, right? So now this network has been constructed which can give you a tower function, right? So I can have a neural network which gives me a tower function, and now I am happy, right? Because that is the tower block is what I was looking for. I have my tower maker now.